Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we are going to learn how to quantify the solubility product constant, which is KSP. And we're also going to learn how to determine the molar solubility of that slightly soluble, mostly insoluble ionic compound. We're also going to learn how to express the molar solubility in different units, such as grams per liter, parts per million, and parts per billion. So hopefully you guys enjoyed this little cartoon that I drew. The little green monster, it's going to be the precipitate, and those blue eyes is just representing the water. So hopefully you guys enjoy that joke. Let's go ahead and get started. For number one, at 25 degrees Celsius, the solubility of silver chloride is 1.34 times 10 to the negative 5. The question is asking us to determine the solubility product for this slightly soluble salt. Okay, and so there's a lot of S's, there's a lot of words with that starts with the letter S. Solubility is tossed around here several times, and so what we want to do is we want to be able to break down this problem and understand what this question is really asking us. And so I'm going to switch over to my yellow highlighter. Here in the first sentence, they're telling us that the solubility of silver chloride is this value. And so whenever the solubility is provided, it's referring to the molar solubility of the slightly soluble salt. So silver chloride is going to be AgCl, and we know that is going to be our slightly soluble salt, mostly insoluble, based on our solubility rules, right? So silver is an exception to chloride's rule of being soluble. And so this word solubility is referring to the molar solubility. And we know it's molar solubility because if you look at the unit, here we have capital M, and capital M represents molarity. So here in this scenario, they gave us the molar solubility, and we want to determine the solubility product. Now, whenever the question is asking about the solubility product, it's asking us to determine the KSP. Okay? And so it can be written such that it's saying determine the solubility product constant, or it can leave the constant out. So either way, the solubility product is KSP. And so the value 1.34 times 10 to the negative 5 is representing solubility, which is going to be abbreviated as S. And so here we have 1.34 times 10 to the negative 5 molar. Okay, and so this is the solubility for silver chloride. And so the first thing that we're going to do to determine the KSP is to write a balanced chemical equation. And by us writing a balanced chemical equation, we can go ahead and build our ice table and then create our mass action expression with respect to the solubility product. And so here if we have silver chloride, and remember whenever you guys are writing the balanced chemical equation for these types of problems, you always want to make sure that your slightly soluble compound is written on the reactant side, and the product side is simply going to be the ions that dissociates from the solid. And here, for every one silver chloride, that produces one silver ion and one chloride ion. All right, so we're going to go ahead and build our ice table to describe the change And so when you guys build this ice table, you'll notice in the problem that there's no initial amount that's given to us, right? And so here they're just specifically saying that the solubility is 1.34 times 10 to the negative 5. And that solubility represents the change, how much of that silver chloride will be soluble to produce those ions. And so we're going to go ahead and write minus S. And however soluble that silver chloride is, that's how much silver ion and chloride ion will be produced. And so in this scenario, there are no initial concentrations. There's simply the value for the change, which is soluble, which is the molar solubility or solubility. Now, at equilibrium, we do get like minus S. So I guess I'll just put it in here for now. However, since this is a solid, we know that we're not going to incorporate this in our mass action expression. I'm simply putting it there just to describe the change that's occurring as we go from the initial state when we drop a solid version of silver chloride in water, and that of the final state at equilibrium. And so we can go ahead and incorporate the coefficient. So plus 1s plus 1s. And here we get plus 1s and plus 1s. Now that we have the expressions for each of these components at equilibrium, we can go ahead and write a mass action expression with respect to the solubility product. And, I'll just go ahead and write it out the first time around. So here we have silver ion raised to the first power times this by chloride ion raised to the first power. And once again, these powers, these exponents, are coming from the coefficient. And the coefficient is of the change is also coming from the coefficient in the balanced chemical equation. Now, since silver chloride here is solid in state, we're not going to include that in our mass action expression. So the KSP is simply equal to 1s, or just s, raised to the first power, times this by s raised to the first power. And what we get is going to be KSP is equal to s squared. And so here we've kind of reduced our terms into something that's very simple. KSP is equal to the square of the molar solubility of our slightly soluble compound. And that's typically the case if it's a 1-to-1 ratio. So if you guys memorize this fact or understand this fact, you technically don't need to write your ice table. However, if your coefficients are different, then you might want to write your ice table so that your work is better organized and you don't make a simple mistake. And so I mentioned earlier that the molar solubility of silver chloride is 1.34 times 10 to the negative 5. And so we're going to go ahead and plug that number into our equation over here, such that KSP is equal to 1.34 times 10 to the negative 5 squared. And so if you plug that into your calculator, I'll go ahead and quickly plug that into my calculator. So I have 1.35 times 10 to the negative 5, and then I'm going to square that value. The KSP is going to be 1.82 times 10 to the negative 10. And so this would be the solubility product for silver chloride if the molar solubility is 1.34 times 10 to negative 5 molar at 25 degrees Celsius. And so if you can imagine, if you change the temperature, typically you'll increase the molar solubility, and therefore the value of the KSP will change. It'll be different than at 25 degrees Celsius. Okay. All right. And so that's pretty much how you guys are going to tackle these types of problems. It's just being able to identify, what you're given and what you need to look for. So let's go ahead and apply that to problem number 2. At 25 degrees Celsius, the solubility of magnesium phosphate is 6.26 times 10 to the negative 6 molar. So we're going to determine the solubility product for this slightly soluble salt. So same idea. Since the solubility is described as 6.26 times 10 to the negative 6 molar. Oh, actually, let me take a step back here. I do want to mention this. Since KSP is an equilibrium constant, therefore it will be unitless. Okay. And so if you guys are talking about the molar solubility, then there is a unit, and that's typically molarity. All right, so at 25 degrees Celsius, the solubility of magnesium phosphate is 6.26 times 10 to the negative 6. So solubility, or molar solubility, is represented by the letter S. And magnesium phosphate has a chemical formula of Mg3 parentheses PO4 parentheses 2. Okay. And so if you guys haven't balanced chemical formulas from the name for quite some time, I really do encourage you to revisit that from the first semester of general chemistry. Okay. And so the solubility of magnesium phosphate is equal to 6.26 times 10 to the negative 6 molar. So notice that there is a unit for molar solubility. And so to determine the KSP, so here it's asking us to determine the solubility product. And so once again, that's referring to KSP. So I'll make sure to highlight that in green, just so it's color-coded. We're going to have to build our chemical equation and write our mass action expression, and then plug in the values that we can plug in. So since our slightly soluble, mostly insoluble salt is going to be magnesium phosphate, we're going to go ahead and write magnesium phosphate on the reactant side. And then you're going to imagine that all of these, you're going to imagine that this chemical formula is just going to separate. And so this is going to tell you that there's a small fraction of it actually ionizing, hence the picture. So here, this picture that I drew, this guy right here is going to be like the precipitate, right? And the precipitate is composed of all of these ionic compounds and ionic salts, cations and anions, etc. And so at equilibrium, some portion of the cations and anions that make up that precipitate will ionize, right? That's described by the molar solubility of the precipitate, producing these little green guys that's trying to get away from the precipitate. Okay. And so if we imagine magnesium phosphate, ionize or separating, we get 3 moles of magnesium plus 2 moles of phosphate. Okay. So that when you guys separate your ionic compound, you need to make sure that you guys are writing the charges. Now we're going to go ahead and build our ice table. And so this ice table is going to help us organize our values. So looking at the problem, question number 2, notice that the problem didn't really indicate how much of the magnesium phosphate we have. It just simply gave us the solubility. And so the solubility is the amount that's going to be soluble. So it's describing the change. And so here we have, so we don't know how much we have, that's okay. And here we have minus S. And since we're just taking our magnesium phosphate and placing them in water, that's like the initial image. We don't have initial concentrations or initial amounts of magnesium and phosphate ion. And so, however, we do know that a certain amount of magnesium phosphate will ionize to produce 3 times the amount that the magnesium phosphate times that by 3 times the solubility, the molar solubility of magnesium phosphate. Okay. And so once magnesium phosphate ionizes, then the molar solubility times 2 is going to represent how much phosphate is going to be released in the solution. So at equilibrium, we have 3S and we have 2S. Oh. All right, so after we write our ice table, we're gonna go ahead and do our KSP thing. So maybe I'll do it over here since I'm running out of room. Oh well. So KSP is equal to, and I'm going to skip some steps. And so it's going to be 3S, which is going to represent the magnesium. And remember that there's a coefficient of 3, so I need to raise this to the 3rd power, times this by 2S, raise that value to the 2nd. And to reduce this, we're going to have to make sure to distribute the exponent to both the number and the letter and the variable. And what we get is going to be 3 to the 3rd power times S to the 3rd power times this by 2 squared times this by S squared. I'm just going to zoom in. And so 3 times 3 times 3, that's going to be 27. Times this by S to the 3rd, times this by 4, times this by S squared. And so your numbers are going to be multiplied together and your variables are going to be added. The exponents will be added. So what we get is going to be 27 times 4. I believe that's 108. Let me just check. Yep. So here we have 108. And then we have S to the 5th power. And that's the expression that we're going to get to determine our solubility product. And so scrolling up, we're trying to solve for KSP, but the value of the solubility, the molar solubility, is already given to us. So all we're going to do is we're going to plug this number into the value, into S. So here we have 108 So 6.26 times 10 to the negative 6 to the fifth power. And so make sure you guys are doing everything in the parentheses first. So 6.26 times 10 to the negative 6. Then you guys are going to raise that to the fifth power in your calculator. And I get 9.61 times 10 to the negative 27. And I'm going to multiply that value by 108. And the value for the KSP that I get when you guys plug all of this stuff in your calculator is going to be 1.04 times 10 to the negative 24. Okay, so that's really, really small. We'll talk about the magnitude of KSP and what that means in terms of the solubility in another lecture video. But for now, all we're trying to do is trying to figure out how we can determine the molar solubility, the solubility product constant from the molar solubility. Okay. And so example number 1 just kind of introduces you on how to set up your calculations when the coefficient is 1, 1, 1. Here the coefficients are not 1, 1, 1. So what would happen if our coefficients were anything above 1, right? How would our calculations look? So that's the main purpose of this example. And so once again, for example number 1 and number 2, they gave you guys the molar solubility, and you're going to determine the solubility product constant from it. All right, so let's go ahead and look at question number 3. So question number 3, we're going to calculate the solubility of calcium fluoride in water if the solubility product is 3.4 times 10 to the negative 11. And then we're going to express the solubility of calcium fluoride in terms of molarity, grams per liter, parts per million, and parts per billion, so ppm and ppb. Finally, we're going to determine the concentration of the calcium ion and the fluoride ion when the equilibrium is reached. Okay. And for the last part, we can actually determine that from the other two problems. So for example, if you guys want to determine how much of magnesium ion and phosphate ion is present in solution at equilibrium, you guys are just going to take you're going to take 3 and multiply it by the molar solubility. So 3 times 6.26 times 10 to the negative 6, or 2 times 6.26 times 10 to the negative 6. And that would give you the equilibrium concentrations of magnesium ion and phosphate ion that's present when equilibrium is reached for after the slightly soluble compound magnesium phosphate has ionized. All right, so let's go ahead and break down what we have. Here we want to calculate the solubility of calcium fluoride. And so we want to determine the value of S. Here in this case, they gave us the solubility product. Notice how there's no unit at the very end because the solubility product, KSP, is unitless. Okay, so that's one way that you guys can differentiate the two. Solubility you'll have some unit for solubility. For solubility product, KSP, there's no unit. All right, so let's go ahead and tackle this problem. So we have calcium fluoride, and so calcium fluoride, so calcium is positive 2, fluoride is negative 1. When you guys put these together, we want to balance the charges, so it's going to be CaF2. Okay. And so here we have calcium fluoride, and since this is our slightly soluble compound, it's going to have the S, the solid designation. And feel free to check the solubility rules. Actually, there's no, I don't think I listed a solubility rule for fluoride, but you guys can actually, so here in the second semester of general chemistry, you guys can actually determine if your compound is soluble or insoluble by looking at the magnitude of your KSP. And so if your KSP is really, really, really low, then its molar solubility is probably pretty low as well, ish. And we'll take a look at that in another lecture video. But long story short, the magnitude of your KSP can give you some idea as to whether or not if it's soluble or insoluble. And so if your KSP is far, far greater than 1, then looking at the chemical equation, so let's think about this. If KSP is far, far greater than 1, then that means at equilibrium, most of your substance will be the ionic form. So that lets you know that it's going to be soluble, right? Where if KSP is far, far less than 1, then you know that the reactants would be favored if KSP is far, far less than 1. And so if your KSP is far, far less than 1, then it's most likely that your compound, your reactant, is going to be mostly insoluble in solution. Okay. All right, so now that we have this chemical equation, so the KSP, I'm going to summarize it here, is given to us as 3.4 times 10 to the negative 11. So notice how this KSP is far, far less than 1, meaning that at equilibrium, we should see the insoluble compound, the calcium fluoride as a solid, predominant in our solution. And we won't see a lot of the products, in this case the ions, in the solution. We'll see some, but not a whole lot. And so here we have calcium, 2 plus 2 F minus. Okay. Oh. Okay. And if we're building our ice table, so reading through the problem, it just says to calculate the solubility if the solubility product is given. And so it didn't really tell you any initial amounts of the reactants or the products. However, it did tell you the KSP, which is 3.4 times 10 to the negative 11. We're going to use that KSP to determine the solubility. And so the solubility, if you guys recall, is represented as S. So some amount of the calcium fluoride is going to separate, it's going to dissolve, producing calcium plus 2 times the amount of calcium fluoride, times that by the molar solubility of calcium fluoride. And so adding down, we have S and then 2S. And so here KSP is equal to the calcium raised to the first times this by fluoride raised to the second power. So if I plug everything in, my KSP is equal to S times this by 2S squared. And so KSP is equal to 4S to the third. Okay. So this part right here is going to be 4S squared. So 4S squared times this by S to the first. You just add the powers together and you get 4S to the third. So now that we've reduced our equation, all we're going to do is plug in 3.4 times 10 to the negative 11. And so 3.4 times 10 to the negative 11, which represents the KSP, the solubility product, that's equal to 4 times S to the third power. And so if I divide the 4 over, okay, so I'm going to do this in my calculator. So I have 3.4 times 10 to the negative 11. Divide this by 4. And that's going to give me 8.5 times 10 to the negative 12. That's going to equal to S to the third. And so you guys are going to cube root both sides. And so if you guys are struggling to do a cube root in your calculator, you can also raise it as an exponent. Okay. So a cube root is equal to whatever it is inside the parentheses raised to the 1/3 power. And so in your calculator, you guys can put the number. What is going on? You guys can go ahead and put the number and then the caret sign to represent the exponent. And then you can put in 1 divided by 3 and then press enter. And that should represent the cube root for that specific problem. All right, so if I take the cube root of 8.5 times 10 to the negative 12, I'm going to go ahead and raise it to the 1/3 power. My value of S is going to be 2.0 times 10 to the negative 4. Now, since I'm talking about solubility or molar solubility, I need to add in my unit. And so what this is basically telling me is that 2.0 times 10 to the negative 4 moles per liter of calcium fluoride, the insoluble, quote unquote, insoluble compound. This is how much will actually dissociate to produce your calcium ion and fluoride ion. And so if you wanted to determine the concentration of the calcium ion and fluoride ion when equilibrium is reached, then all you will have to do is take the molar solubility, which is S, and plug that in to your equilibrium value. Okay, so let's go ahead and do that. So at equilibrium, the concentration of calcium is represented by S, or 1S, 1 times the molar solubility of calcium fluoride. And so that's just going to be 2.0 times 10 to the negative 4 molar. Okay, so this is how much of calcium ion that we'll get at equilibrium. And so for the fluoride ion, it's going to be 2 times S, so it's going to be 4.0 times 10 to the negative 4 molar. And so, okay, well, technically speaking, if we use the whole value, if we use the whole number, it'll be 4.1 times 10 to the negative 4. And so when you guys punch this into the calculator, you'll see that it's 4.081655 times 10 to the negative 4. That's the product of you multiplying by 2. So if you round to 2 sig figs, it'll be 4.1. So you're rounding the 8 up. And so this is going to be the molar concentration of fluoride ion at equilibrium. Okay. And so we went ahead and basically answered this question. And so the next thing that we're going to, actually we also answered this question. We calculated the solubility. So the solubility of calcium fluoride is 2.0 times 10 to the negative 4 molar. And so the next thing that we're going to do is we're going to express the solubility of calcium fluoride in molarity, grams per liter, parts per million, and parts per billion. And so our answer will always naturally be in molarity. And so we've already determined the molar concentration of calcium fluoride that's going to represent its solubility. Next, we're going to convert this into grams per liter. And so if the molar solubility of calcium fluoride, just write it up here. So calcium fluoride, its molar solubility is 2.0 times 10 to the negative 4 molar. To convert this into grams per liter, we have to think about how we can break down molarity. So molarity, if you guys recall, is moles per liter. And so if you guys can convert moles into grams, then you guys have your units in grams per liter, which is what the question is asking. And so to do that, I'm going to put moles at the bottom to cancel out that unit. And since I want to go from moles to grams, I'm going to put grams at the top. So if you guys have grams per mole as your unit in your dimensional analysis, this is referencing that you should use the molar mass. So you guys need to calculate the molar mass of calcium fluoride. And that's what you guys are going to use for your stoichiometric ratio. And so to determine the molar mass of calcium fluoride, we're going to go ahead and list down our elements. And we have 1 calcium for 2 fluorides. For calcium, we have an atomic mass of 40.078 grams per mole. And for fluorine, we have 18.998. So 18.998 grams per mole. And so you guys are just going to multiply across and then add your results. And so if you guys want to see this kind of like tabulated in your calculator, okay. Okay. You guys can go ahead and think about it this way, where this is going to be calcium and this is going to be fluorine. Now real quick, for your molar mass, I personally would like all of my students to record to 3 places after the decimal. If you guys round up, it's not actually going to change your answer, like the actual value of it. It's not going to change it off, but it's not going to change it too much. The reason why you guys want to report more significant figures is because you don't want your molar mass to limit the number of significant figures that you're going to report in your final answer. And so the molar mass in your periodic table, and I personally use the Van Bramer periodic table. So the Van Bramer periodic table, and you guys can Google that in, and you guys can click on the PDF and download it for yourself. I should have uploaded a copy in your Canvas course. So your Van Bramer periodic table, those values, most of those values, the atomic masses, they're much more precise than your actual instrument. And so your instrument of measurement, if you're talking about mass, is like a balance scale or an analytical balance. And if you recall, your analytical balance, your balance scale, is about 2 to 3 places after the decimal. And so you just want to make sure that your molar mass does not limit the number of significant figures in your final answer. So anyways, I'll go ahead and plug this in my calculator. So I have 2 times 18.998, and I'm going to go ahead and add 40.078. And so that's going to give me a molar mass of 40. So I'll just put it down here. Actually, I'll put it right here. So here I have 78.074 grams per mole. Okay. And remember, you guys can always extend that unit, and that's letting you know that the number 78.074 belongs to grams, and the 1 belongs to mole. And so I have 78.074 over 1. Okay. And so I can go ahead and multiply those two values, and that's going to go ahead and give me the number of grams for every single liter. Okay, so notice that my liter and my grams are the only two items that are still present in my calculation. So here I have 1 point, so I'm going to round it to the correct number of significant figures. That's 2 in this case, so 1.6 times 10 to the negative 2 grams per liter. Okay. And so this is the molar solubility of calcium fluoride in grams per liter unit. And so, one can imagine that if you express this scientific notation, so that's 2 places to the left, that's 0.016 grams for every liter. And so sometimes expressing the molar solubility in grams per liter gives you an idea that you can kind of like measure it out in lab. Not that you would, but mass is typically expressed in grams, which you guys can measure out using a balance scale or an analytical balance. And volume can be, you guys can use a volumetric flask or a graduated cylinder to measure out 1 liter, right? And so this gives you more of a roughly better idea of the molar solubility if it's expressed in terms of grams per liter. At least it does for me. All right, so now that we've expressed this in grams per liter, okay, we're going to learn how to express this in parts per million and parts per billion. And so parts per million and parts per billion, it's another unit of I guess to express the amount of the substance for certain unit of volume. And let me see here. So I'm not going to go through the whole derivation of parts per million, parts per billion. I'm just going to go ahead and tell you that parts per million is the same if you have your units expressed as milligrams per liter. And parts per billion is expressed in micrograms per liter. So what I'm trying to basically tell you is that you can determine the parts per million and parts per billion if you can express your units in milligrams per liter. So once you guys have in milligrams per liter, that is ppm. And micrograms per liter, that is ppb. And so I'm going to take that 0.016 grams, so 0.016 grams per liter, and I'm going to do a prefix conversion. And so I'm going to put grams at the bottom, milligrams at the top, so that way those two cancel. And then if you noticed, my final unit is going to be milligrams per liter, which equals to a ppm. And so since it's a prefix conversion, you guys can say that for every 1 gram, that's going to be 1,000 milligrams. Okay. And so if you multiply that by 1,000, you're going to move this decimal place 3 times to the right. And so what you get is going to be 16.0 milligrams per liter. And so once you guys get 16 milligrams per liter, that's equivalent to saying 16 ppm. So there's 16 parts of calcium fluoride per million. Okay. Now to calculate ppb, the goal is for us to convert this 0.016 grams per liter into micrograms per liter. Oops, not per liter. Micrograms, grams at the bottom. Sorry, so I'm trying to cancel out my unit of grams, and I need to think about my conversion. Okay, and so in this scenario, I'm actually going to put 1 for my prefix. So what does 1 microgram equal to? Well, a micro represents times 10 to the negative 6. So 1 microgram is equal to 1 times 10 to the negative 6 grams. Okay. And so if I plug that into my calculator, 0.016 divided by 1 times 10 to the negative 6, that's going to give me 1.6. Wait, hold on. Sig figs. Sorry. So that's going to give me 1.6 times 10 to the positive 4 micrograms for every liter. And I can go ahead and convert micrograms into ppb. So they're equivalent expressions. And so my final answer for the solubility, I apologize, for the solubility of calcium fluoride in terms of ppb is going to be 1.6 times 10 to the positive 4. Okay? All right. And so hopefully you guys understood that, the conversions of ppms, ppbs, grams per liter, etc., etc. So that's all coming from general chemistry, first semester general chemistry. All right, so number 4, we're going to calculate the solubility of manganese to iodate in water if the solubility product is 4.37 times 10 to the negative 7. And so feel free to pause this video, try to do this one on your own, and then feel free to play this video and maybe fast forward my explanation. But for those who want me to work this problem out, I'll go ahead and do it. But feel free to stop this video at any time and just do this yourself, just to see if you guys are getting the concept down. And so it's the same situation as number 3. We're just switching out the solubility product and the identity of the compound. So here in this case, we want to calculate the solubility. So we're going to figure out what S is of manganese to iodate. So manganese is Mn. This 2 means 2 plus. Iodate is IO3, negative 1. So when you combine both these ions together, you get Mn parentheses IO3 2. Okay. And so if you look at the solubility product constant, it's times 10 to the negative 7. Since the solubility product constant is far, far less than 1, I know that my manganese 2 iodate is going to be mostly insoluble. Okay. And so what that tells me is that to figure out my solubility, I'm going to go ahead and write that slightly soluble, mostly insoluble compound on the reactant side. And then I'm going to write my resulting products if these guys ionize. So I have 1 of Mn and then 2 plus aqueous, and I have 2 moles of the iodates. Okay. So remember, these coefficients, I'm just grabbing it from the subscripts. For every 1 manganese, I have 2 iodates. And so the KSP, or the solubility product, is going to be 4.37 times 10 to the negative 7. Okay. And so once again, build my ice table. This problem didn't really state that you have an initial amount for reactants or products, so there's going to be minus S plus 2S. So at equilibrium, we're not really going to express this at equilibrium, but we can if we want. But it's not going to be expressed in our mass action expression. Let's see here. So here we just have S and then 2S. So therefore the KSP is equal to, I'm going to skip some steps. It's going to be S raised to the first power times this by 2S raised to the second power. And so if I were to simplify this, we get 4S to the third. And that's going to equal to the value of KSP, which is 4.37 times 10 to the negative 7. So 4.37 times 10 to the negative 7. And so to figure out S, I'm going to go ahead and take that value, 4.37 times 10 to the negative 7, and then divide it by 4. So 4.37 times 10 to the negative 7 divided by 4. Then that's going to give me 1.0925 times 10 to the negative 7. And to get rid of that third, that exponent, I'm going to go ahead and cube root both sides. And so I'm going to raise my answer. So I'll go ahead and just write this down. So 1.0925 times 10 to the negative 7. And since I have 3 sig figs here, I'm going to keep my first 3 sig figs just to remind me. And so I'm going to raise this to the 1/3 power, 1 divided by 3. And the value that I get is going to be 4.78 times 10 to the negative 3. And so the molar solubility of manganese iodate is equal to 4.78 times 10 to the negative 3 molar. Okay. And so if you guys look at the molar solubility between the two compounds that we just solved for, so the molar solubility for calcium fluoride is 2.0 times 10 to the negative 4. And so that negative 4 is a lower value than times 10 to the negative 3. And so if you're trying to compare the molar solubilities, it looks like manganese 2 iodate will be more soluble in water than calcium fluoride, right? So if you guys are comparing the molar solubilities directly, you can determine which one is more soluble in water compared to another. And I'll discuss that in another lecture video. I just thought I would bring that up here. All right, cool. So now that we figured out the molar solubility, in molar concentration. So I figured this out, I figured this out. I'm going to go ahead and express this in grams per liter, ppm and ppb. Okay. So here I have 4.87 times 10 to the negative 3. 4.78 times 10 to the negative 3. And molarity is going to be broken down into moles per liter. And so I'm going to express this same value in grams per liter. So to do that, I'm going to cancel out the moles by putting it at the bottom. And I'm going to convert it to grams. So grams per mole. And that's inviting me to figure out my molar mass. And so you guys can go ahead and use the periodic table to figure out the molar mass of manganese iodide. Here in this case, I have 1 manganese and then I have 2 iodines, so don't forget to distribute that too. And then here I have 6 oxygens. And I'm going to multiply the amount by its atomic mass that's found in the periodic table. And once again, I'm using the Van Bramer periodic table, and I'm going to record 3 places after the decimal. So here I have 54.938. And for iodine, I have 126.904. And oxygen is going to be 15.999. Okay. So you're going to multiply them and then add everything. So I'm going to go ahead and do that quickly in my calculator. So I have 54.938 plus 2 times 126.904 plus 6 times 15.999. And that's going to give me a total molar mass of 404.740 grams per mole. All right. And so make sure that, so you guys can go ahead and rewrite grams per mole in terms of grams per mole like this, and then extend that line, letting you know that the 404 belongs to grams, not moles. And so I'm going to go ahead and multiply those two. So I'm going to multiply that by 4.78 times 10 to the negative 3. And what I get is 1.93 grams per liter of manganese iodate. And so this is telling me that 1.93 grams of manganese iodate will actually dissolve per liter of that solution. So that's quite a bit compared to calcium fluoride, right? So if you look at calcium fluoride, what was its? It was 1.6 times 10 to the negative 2 grams per liter. I'm sorry, that shouldn't be molar solubility. That should just be solubility. Okay. So the solubility of manganese iodate in water at 25 degrees Celsius is going to be 1.93 grams per liter. So that's a lot more than calcium fluoride. So to express this value in parts per million and parts per billion, we're going to go ahead and do some prefix conversion. So we're going to go from grams to milligrams if I want to determine the parts per million. And so for every I can also do this too, right? So if you guys don't know the whole thousand and the thing, so a milli is times 10 to the negative 3. So if you have 1 milligram, how many grams do you have? Well, a milli is times 10 to the negative 3, so you can put in 1 times 10 to the negative 3 grams is equal to 1 milligram. Now, if you guys didn't like that, that's fine. You guys can go ahead and put in 1,000 milligrams, that's equal to 1 gram. Both will give you the same answer. And so if I'm going to multiply the value by 1,000, I'm just going to get 1,930 milligrams per liter. And so I have 1,930 parts per million. Okay. And if I wanted to express this in terms of parts per billion, I'm going to convert it into micrograms. So grams will cancel. So if I have 1 microgram, a micro is times 10 to the negative 6. And so I'm just going to take this decimal and move it 1, 2, 3, 4, 5, 6 times to the right. And you guys can do that in your calculator and you'll get the same answer. Okay. And so hopefully going through this exercise, you guys can you guys understand how to go from grams per liter to milligrams per liter, which is the same thing as ppm. And this is going to be micrograms per liter, which equals to ppb, parts per billion. So here we have 1,9. I'll just do this in scientific notation. So 1.93 times 10 to the positive 6 ppb. Okay. Oops. All right, so we finally finished doing all 4 of these. And so the last thing that we're going to do is determine the concentration of manganese ion and iodate ion when equilibrium is reached. And so if you guys look at the ICE table, the equilibrium concentration for manganese is defined as S. And if you guys look at the ICE table, the equilibrium concentration for iodate is defined as 2S. Okay. And so you guys can just go ahead and do this one on your own. I won't calculate it out. But you guys are going to take the value for S. And so here, I'll do this in a different color. S, or the solubility, is 4.78 times 10 to the negative 3. So you guys are just going to plug that into here, plug that into S, and then multiply that by 2. Okay? And that would give you your molar concentration of manganese and iodate. All right, so hopefully going through these 4 examples, you guys understand how to either 1, figure out the molar solubility from KSP, and 2, figure out the molar solubility if you're given the KSP. Okay. All right, so we're going to go ahead and move on to the next topic of this chapter, which is common ion effect. I'll see you guys in the next video.